section, we're going to be discussing these characteristics of variation, the measures of dispersion. So, well, why? Let me do the following example. So, the grade on an exam is determined as follows. A is the upper 10% of the scores. So if you're in the upper 10% of the scores for your class, you get an A. B, if you're in the next 15% of your scores. C, if you're in the next, if you're in the middle 15%, 50% of the scores. D, if you're in the next 15% of the scores. F, if you're in the bottom 10% of your scores. So suppose, now this is actually a very common way of curving scores. So when people curve scores, it's usually looking something like that. This is very common. So suppose you take an exam and you get a score of 72 on the exam. So 72% on the exam. And the average for the class on this exam was 70. What is your grade? So you got a 72 and the average was 70. What's your grade? So if we only need to study measure central tendency, I should be able to figure out your grade from this. Well, what do people think? You got a 72 on your exam? What do you think your grade is? And the class average was a 70. So, anyone? If you get a 72? Okay, not a lot of, no one's volunteering. Anyone want to volunteer? A guess. What do you think? Well, the answer is, I don't know. If your distribution, and this was actually done on a computer, so that it actually is what it says it is. So if the distribution does look like this, and you got a score of 72, you actually get an A in your course, in this exam. Whereas, if your distribution looked like this, you got a B. Whereas if your distribution looked like this, you got a C. So it really depends on what everyone else in the class did. So depending on what everyone else did in class, you could either get an A, B, or C. You can't get a D because you're above. So I know you don't have a D or F because you're above the middle. So you're above the average. So because you're above the average, then I know that you're either A, B, or C. But I don't know which one of them. So you got, all I know is if you got a 72, you got a C, at least a C. So that's what I know. I know you didn't get D or F. But other than that, I can't tell you if you got A, B, or C. When I was an undergrad, I took a course in biology, and on the first exam, the first exam was multiple choice. They gave you 50 questions, and you filled in, they're all multiple, so they're 50 multiple choice questions, and you filled in, the Scantron, where you just filled in the bubbles, and then they scored it to you, and they gave you back what your score was, and then they told you what that corresponding grade would be on that exam. On my first exam, I got 49 out of the 50 correct. But with the curve, I got a B. So the curve was, if you got one wrong, actually it was A turned out to be 100%. Right? B was if you got, I think it was 45% to 98%. So I was at a B, but just B. so you know, I could have gotten half the oh, and of course, then they when they did this, they only did A, B, and C. So the fact you got 98% didn't really affect it. You got a B on that exam. So a 45, if you would have gotten anything like a 45 to 98, you got the same grade on the exam. So I was not that happy that I mean, I thought I did better than that. Okay, so you live and die by a curve. You live and die by what everyone else does in class, not by what you do. Okay, so so in order to determine the grade, you must know the spread of the data. You must know the dispersion of the data. So let's look at some measures of dispersion. The range. And so the range is just the maximum value minus the minimum value. So suppose that I have the following set of data: 4, 5, 8, 12, 17, 24. Then the range is, well, 24 minus 4 is 20. So the range is very sensitive to these extreme values. They're the only two values that you take, are the most extreme at both endpoints in both directions. So it's not very useful. So it's not a very useful measure of dispersion unless you don't know a lot about your what's happening with your data. If you don't know a lot about your data, then a lot of times it's very easy to calculate your range. And then from there, and we'll see later on, using the range rule of thumb, we can give a very nice estimate of a measure of dispersion. So if you don't know a lot, then the range is a good measure of dispersion. If you know your data, then you don't use the range. Quartile deviation. So I'll be explaining the quartile deviation more in the next section. But let me just say what it is, and then in the next section, I'll actually explain what each of these mean. So the interquartile range is the difference between the third quartile and the first quartile. The quartile deviation, which is our measure of dispersion, is sometimes called the semi-interquartile range. It is half of the interquartile range. It is third quartile minus first quartile divided by 2. So it is the middle 50% of your data. Okay, so recall from the previous section. All right. Previous, I should have really said. Above doesn't make sense. So the previous discussion we had on the following rules of thumb. We said that for any distribution, the sum of the absolute deviations from A is minimized when A is the median. So if we want to measure dispersion from a median, then we should use the absolute deviation from the median. So let's define the sample median absolute deviation. The sum of the absolute value of x minus the mean, minus the median, all divided by n, where n here is the sample size. The population median absolute deviation is the sum of the absolute value of x minus the population median, all divided by the population size. So let's do the following example. Let's determine the median absolute deviation for the following set of data: 4, 9, 5, 4, 5, 9, and we'll be using the Weibull method. So the data has been sorted for us. There are 3 numbers, so n is 3. So 3 plus 1 is 4, divided by 2 is 2. So the median is the number in the second position, 5. So let's find the median absolute deviation. Let's subtract 5 from each of these. Take their absolute values. 4 minus 5, 1. 5 minus 5, 0. 9 minus 5, 4. Again, I'm taking the absolute value of the differences. Let's add them up. 1 plus 0 plus 4 is 5. Divide by however many numbers there are, 3. Therefore, the median absolute deviation is 5/3. Sometimes we will compute, but you really shouldn't compute the absolute mean deviation. The sum of the absolute value of x minus the mean all over n. For population mean absolute deviation, the sum of x minus mu over n. And the sum of x minus mu, take the absolute value. So the sum of the absolute value of x minus mu, all divided by n. Determine the mean absolute deviation for x equaling 4, 5, 9. So let's find the average. 4 plus 5 plus 9, 18 divided by 3, 6. So let's subtract 6 from each of these and then take its absolute value. So 4 minus 6, negative 2, absolute value is 2. 5 minus 6, negative 1, absolute value is 1. 9 minus 6, 3, absolute value is 3. Add them up, so that's 6 divided by 3 is 2. Note that the median absolute deviation is always less than or equal to the mean absolute deviation. So the measuring of dispersion from a mean is not should not be calculated by looking at the mean absolute deviation. It is not preferred. However, if you're going to be measuring dispersion from a median, then the measure of dispersion that is preferable is the median absolute deviation. If I want to measure dispersion from a mean, then I should do the following. Well, recall that, so from the previous, I shouldn't say above. So recall from the previous discussion on the properties of the mean that the sum of the deviations from the mean is always equal to 0. So that's not a good measure of dispersion because it doesn't give us, doesn't distinguish between between any of the differing sets of data. So for any distribution, the sum of the square deviations is minimized when A is the mean. And so that means that I should look at, if I'm going to be looking at a measure of dispersion from the mean, in this case the sample mean, that I should look at the sum of the square deviations. Similarly, recall that for a population mean, the sum of the dispersions from the mean was also from mu was 0. And just like above, the sum of the square deviations from A is minimized when A is equal to mu. So again, I should be looking at the sum of the square deviations if I'm going to be looking at a measure of dispersion from a mean. So I should not be looking at this for a mean. So this is not, I should not be using a mean absolute deviation. Okay, so before I can tell you how I should define the measure of dispersion for both a sample and for a population, let me give you an example involving degrees of freedom. So carbon monoxide is measured in San Francisco on 5 different days. And the mean of those 5 values is 0.62 parts per million. 4 of the values in parts per million are 0.3, 0.4, 1.1, 0.7. The data are from the California Environmental Protection Agency. So first, A, find the missing value. B, we need to create a list of n values that have a specific known value. We are free to select any values we desire for some of the n values. How many of the n values can be freely assigned before the values are determined? The result is referred to as the number of degrees of freedom. So let's find the missing value. Let y be this unknown value. So I have here 0.3, 0.4, 1.1, 0.7, some missing value. Let's call it y. So let y be the unknown value. Then the mean, the sum of x over n, is, well, they tell us, 0.62. And we can find it by just adding up all these values, 0.3, 0.4, 1.1, 0.7, plus this missing value, y. I don't know what it is. I'll just say y. All divided by, there's 1, 2, 3, 4, 5 values. So divide by 5. If I add up 0.3, 0.4, that's 0.7 plus another 0.7 is 1.4 plus 1.1 is 2.5 plus y over 5. Cross multiply, let's multiply both sides of my equation by 5. So 3.1 is equal to 2.5 plus y. Subtract 2.5 from both sides. So y is equal to 0.6. So that missing piece of data here was 0.6. So it should have a 0.6 here. So looking above, well, we can do the same thing, right? If I know in general the mean, I know there's n of these, I know the value of these n minus 1 values, I can determine this unknown value by doing the same thing. So we can let n minus 1 values be freely assigned along with the sample mean, and then we can determine the remaining value. So I have that x equals the sum of x over n, which is just the sum of x over n. Let's multiply both sides of my equation by n, just like what I did here. And so, and then let's bring this value to the other side, which was the sum of all these values here, the sum of the remaining n minus 1 values. And so, let's say I have x sub I is one of them I want to determine. So x sub I is equal to n times the sample mean minus x1 minus x2, minus x sub I minus 1 minus x sub I plus 1 minus x sub n. So I've determined the value of x sub I using all this other data. So my degrees of freedom with a given mean only n-1 values can be freely assigned any number before the last value is determined. There are n-1 independent values. So my degrees of freedom, we will usually denote degrees of freedom as this Greek letter mu is n-1. Sometimes people write df for degrees of freedom, but mu is much more common. So note, let's try to calculate n times the sum of x minus the mean quantity squared. Remember, we're going to be looking at the sum of the squared deviations from the mean. So maybe I want to simplify this first. The reason for putting n out there is, well, I know at the end that if I put n out there, I won't have to deal with fractions. So this is sort of, the n is there because without it, I tried to do the calculation and made it look weird. Didn't make it as nice. So I'll put the n outside. Okay, so let's try to simplify this. So first, I have x minus the mean squared. Well, to simplify that, I just have to use the special product formula. So again, one of the most useful things from your, high school and your junior high is these special product formulas that you memorized. So hopefully when you first saw these in junior high, it was emphasized that you will need to know these special product formulas because they're very useful and they're used a lot. And so I have n is equal to the sum of, well, use the special product formula, x squared minus 2x, x bar plus x bar squared. Now let's use the properties of summation to simplify this. So this is just equal to the fact that the summation is a linear transformation. This is just the sum of n, well, n times the sum of x squared minus n times the sum of 2x x bar plus n times the sum of x bar squared. Again, 2 and n are constant, 2 and x bar are constant. So I'll bring those out in front of my summation. And x bar squared is a constant, so I'll bring it out in front of my summation. So by the property of summation, we have that these are equal. Next, the sum of 1 is n. X bar is the sum of x over n. X bar is the sum of x over n. So I have here n times n is n squared. The sum of x over n is just the sum of x quantity squared over n squared. These n's cancel. So I just have 2 times sum of x times sum of x. So that's the sum of x quantity squared. The n squares cancel. So this last term is just the sum of x quantity squared. But now I have one of these minus 2 of them. Give me minus 1 of them. And so I have that this is equal to n sum of x squared minus the sum of x quantity squared. And so I've shown that this is equal to this. So let's divide both sides of my equation by n. So I have the sum of x minus x bar squared is n. Sum of x squared minus the sum of x quantity squared all over n. So now I can explain where we get this. So the sample standard deviation. So now let me define the sample standard deviation. The sample standard deviation will be denoted by SD for standard deviation. x, and there'll be a lower case x to indicate that it's a sample. Or we could denote the standard deviation by the letter S. It's defined as the square root of the sum of x minus the sample mean squared, all divided by my degrees of freedom. Now, well, the sum of x minus x bar squared from above is this. So I can rewrite my standard deviation in the following simplified computational formula. And so this nice simple computational formula is the square root of n sum of x squared minus the sum of x quantity squared over n times n minus 1. So where my degrees of freedom here is n minus 1. The variance will just be the square of the standard deviation. And so my sample variance is denoted by VAR, and I'll have a little lowercase x to denote the fact that it's a sample standard deviation. It's denoted by S squared also, but you can also say that that's its definition. It's just the standard deviation squared. So it's equal to this without the square root. So just think of what's inside the square root. That's the sample variance. Or let's say you do the simplified computational formula. It's what's inside here is the variance. Inside the square root is the variance. So note, the standard deviation is a measured variation of all values from the mean. The value of the standard deviation is usually positive. It is never negative. The value of the standard deviation S can increase dramatically with the inclusion of one or more outliers. These are data that are far away from all the other values. And the units of the standard deviation are the same as the units of the original data values. So let's use both formulas to find the standard deviation of chocolate chip counts. 12, 7, 11, 9, 8. So let's use this formula first, and then this formula next. So the sum of x minus x bar squared over nu. So I got to figure out what x bar is. I got to figure out what nu is. So let's figure out first x bar. So the sum of x over n. So 12 plus 7 plus 11 plus 9 plus 8, 47, over 5, 9.4. Degrees of freedom is just how many data there are, n, 1, 2, 3, 4, 5, minus 1. So now I want to figure out the sum of x minus x bar squared. Well, x bar is 9.4. So I'm going to take each of these data values, subtract 9.4 from them, square them, and add them up. So 12 minus 9.4 squared, plus 7 minus 9.4 squared, plus 11 minus 9.4 squared, plus 9 minus 9.4 squared, plus 8 minus 9.4 squared. 12 minus 9.4 is 2.6, square that. 7 minus 9.4, negative 2.4, square that. 11 minus 9.4, 1.6, square that. 9 minus 9.4, negative 0.4, square that. 8 minus 9.4, negative 1.4, square that. Add them up, get 17.2, divide that by 4, you get 4.3, take the square root of that, you get 2.0736441353. let's do the simplified computational formula. So let's add up all my data values. 12 plus 7 plus 11 plus 9 plus 8, 47. Add up the squares of each of these numbers. 100, so 12 squared, 144, plus 49 plus 121 plus 81 plus 64, 459. So n, 5, sum of x squared, 459, minus sum of x, 47 squared, divided by n, 5, times n minus 1, 4. 5 times 4 is 20. 5 times 459 minus 47 squared is 86, divided by 20. 4.3, take the square root of that. 2.0736441353. So you may notice that this is much easier than this computation. So in general, it's an easier computation to deal with. So note, well, again, n times the sum of x minus mu squared by the special product formula. X minus mu squared is just x squared minus 2x mu plus mu squared. Using the fact that the summation is linear, this is equal to n times the sum of x squared minus n sum of 2x mu plus n sum of mu squared. Again, using product summation, the fact that 2 and mu are constant, I'll bring them out in front of the summation. The fact that mu squared is constant, I'll bring it out in front of the summation. The sum of 1 is n. Mu is equal to the sum of x over n. Mu is equal to the sum of x over n. The n's cancel. And so I just get 2 minus 2 times the sum of x times the sum of x, the sum of x quantity squared. I get here n times n is n squared. Sum of x over n is just the sum of x quantity squared over n squared. The n squares cancel, so I just get the sum of x quantity squared. Minus 2 of the sum of x quantity squares give me minus 1 of the sum of x minus x quantity squared. Therefore, dividing both sides of my equation by n, I get that the sum of x minus mu squared is n, sum of x squared minus the sum of x quantity squared, all over n. So the variance is the sum of x minus mu squared over n, which is, well, and of course, no, you don't know what the variance is yet, but in a second, I'll tell you what it is. So let's just say that this is in 2 seconds, you know what this is. So the sum of x minus mu squared over n is equal to n, sum of x squared minus the sum of x quantity squared over n squared. Divide each of these by n squared, so it's n, sum of x squared over n squared, sum of x quantity squared over n squared. The n's cancel, so the sum of x squared over n, expected value of x squared. The sum of x over n quantity squared is the same as squaring the numerator and denominator, but the sum of x over n is expected value of x squared. And we'll be calling in about 2 seconds this quantity here the variance of x. So I've shown that the variance of x is expected value of x squared minus expected value of x quantity squared. And that turns out to be an extremely important formula, one of the top 2 or 3 formulas in this course. So know this formula. It's very important. So population standard deviation. I'll denote a population standard deviation as SD, in this case, capital X, to denote the fact that it's a population, is equal to the Greek letter sigma. So I will denote the population standard deviation also by this Greek letter, lowercase sigma. is the square root of the sum of x minus mu squared, all divided by n. By the simplifying computational formula, it is the sum of n. It is the square root of n times the sum of x squared minus the sum of x quantity squared over n squared. Population variance. Well, you just square the standard deviation. So the variance of x, denoted by VAR, capital X, so that I know it's a population variance, is equal to, can also be denoted by sigma squared, again, lowercase, the lowercase Greek letter sigma squared. It is the sum of x minus mu squared over n, or if you want to use the simplifying computational formula, it is n sum of x squared minus the sum of x quantity squared, all divided by n squared. So the sample variance, S squared, is an unbiased estimator of the population variance, sigma squared. This means that S squared tends to target the value of sigma squared instead of systematically tending to either overestimate or underestimate the value of sigma squared. So notice that in the definition for population, we're dividing by n, but in sample, we're dividing by n minus 1. The question is, why are we dividing by n minus 1? Well, that was that degree of freedom thing that we're talking about. So the rationale is that there are only n minus 1 independent values. With a given mean, only n minus 1 values can be freely assigned. Any number before the last value is determined. So dividing by n minus 1 yields better results than dividing by n. It causes the sample variance to target the population variance, whereas division by n causes the formula would cause S squared to underestimate sigma squared. So suppose I had the following example: 6, 10, 4, 7, 11, 6, 12, 6, 5. Compute S. Okay, so let's do this. I'm a TI 83. Okay, so let's input my data. So 6, 10, 4, 7, 11, 6, 12, 6, 5. Let's input that into L1. And let's find its standard deviation. So list, math, standard deviation of L1. 2.833. Let's go to Excel. I did start up Excel, so that's the startup will take a second. Okay, there. Excel. So let's input some data. So let's call this X. 6, 10, 4, 7, 11, 6, 12, 6, 5. And let's call this X. So let's call this guy here X. Okay, so let's find the standard deviation. standard deviation. And let's do it for a sample. .833, 2.8333. And so that's my standard deviation for this set of data.
Professor,
yes, question.
Sorry, on Excel, there are 3 different standard deviation. I know one is for sample, another one for population, but what's the third one for?
Oh, I don't know. Let's see. Like 3 of them? I think that's if you're missing data. I'm not sure. I'm not sure what that third one is. Wait 1 second. Let me see. Which one is that third one? I think A usually means if. What makes it different? Huh. I don't know what makes a difference. Measure how wide this person. I've never used the dev A, and it seems to have the same exact definition as S. I think this is an old, I think the answer is this is an older. So I think this is just an older. So the answer is, I think this is just an older version. Sorry, I'm looking up in Microsoft's documentation. To me, it just seems like it's an older version of the same thing. So if I look, the answer is, I don't think it makes it, I think this is just an older version. Yeah, it's an older version of the new one. So the new one is with the S.
We should use a sample and population for standard deviation, depending on what data.
Yeah, use the S one, because the A, if I remember way back when, that was an Excel 4 or something. So, because it used to just be, if you did it without the S in the old version, let's see if they do it. That used to give you the population. Oh, no. Okay, so now they changed it. So it used to be that this gave you the population standard deviation, and then the other one gave you the sample standard deviation in the old version. So the answer is don't use them anymore. Use the new one where they have the .s. So use the newer version. So does it make a difference? No, but that means that eventually that any formula that you do with the older ones, eventually they're going to get rid of those, and then your formula won't work anymore because they won't have that function anymore. So these are just the latest versions. Okay. Let's see, what else did I do? Excel, Mathematica. Let's go to Mathematica. There's Mathematica. So let's call this something. 6, 10, 4, 7, 11, 6, 12, 6, 5. Oops. And let's not echo this. And standard deviation. Oh, of course, this will give you exact value. Oh, 17 over 6. Oh, okay, so the exact value is 17 over 6. 8 through the degree. Maybe R. Let's do R. Let's call this something. Let's call it X. And let's input all this stuff. 6, 10, 4, 7, 11, 6, 12, 6, 5. Okay, and let's find the standard deviation. 2.83. Okay. There it is. We have so many things open, it's hard to figure out where documents are. Okay, so I could also do it by hand. I'll do it by hand using the simplifying computation formula. So I'll list down all the numbers. 6, 10, 4, 7, 11, 6, 12, 6, 5. Add them up, 67. Square them. So 36, 100, 16, 49, 121, 36, 144, 36, 25. Add these up, 563. So there are 2, 4, 6, 8, 9 numbers. So n is 9. Sum of x squared, 563, minus sum of x, 67. Square that, divided by 9 times 9 minus 1, 8. So 578 over 72. Take the square root of that. So you get 17 over 6. And so 2.8 through the 3. Coefficient of variation. So the coefficient of variation is defined as S over the mean. So the standard deviation over the mean, and you write it as a percent. So the sample standard deviation over the sample mean times 100%, or if you're doing for a population, it's the population standard deviation divided by the population mean times 100%. So sigma over mu written as a percent. Pearson's index is skewness. 3 times the quantity, x bar minus the median, all divided by the sample standard deviation S. Let me give you some properties of the standard deviation. Sigma is less than or equal to R. So R here is the population range. Since the minimum value, since X is between the minimum value and the maximum value of your data, then let's add these all up and divide by n. Well, if you add these all up, all these n numbers, add them all up, divide by n, you still get the same number. Add them all up, divide by n, you get mu. Add these all up, they're constants. Divide by n, you get the maximum. Therefore, mu is between the minimum and maximum value. Therefore, subtracting x from each of these and taking the absolute value, you have that x minus mu in absolute value is less than or equal to the range. Therefore, sigma squared equaling the sum of x minus mu squared over n. Well, each of these are less than or equal to r. So this is the sum of, this is less than or equal to the sum of r squared over n. I can take the, if I'm adding up a whole bunch of the same numbers, well, it's just how many numbers there are, n times r squared over n. The n's cancel, this is r squared. Therefore, sigma is less than or equal to r, taking the square root of both sides of your inequality. And so, similarly, s squared is less than or equal to n divided by n minus 1 times r squared, where r in this case is the sample range, so the range of all your sample values. So in other words, taking square root of both sides of this inequality, the s is less than or equal to the square root of n over n minus 1 times r. Note, however, that for most data, S is actually less than or equal to R over 6. So again, we have that S squared is equal to the sum of X minus the mean, sample mean, squared, all divided by n minus 1. That's the definition of the sample variance. And so we have here that this is equal to the sum of, is less than or equal to the sum of, well, each of these are less than or equal to R in absolute value. And so this is less than or equal to the sum of R squared over n minus 1. Again, you're adding up a whole bunch of constants. So this is just n times the sum of R squared over n minus 1. Take the square root of both sides of the equation. And so I get that S is less than or equal to R times the square root of n over n minus 1. And that's what you want to show. Next. S is equal to 0 if and only if all observations are the same. So if you're doing some measure of dispersion, certainly if all of the data values are the same, then there should be no dispersion. So I certainly want that this is a true statement. That if all the data values are the same, there's no dispersion. And if there's no dispersion, then all the data values are the same. Otherwise, this is not a very useful concept of a measure of dispersion. That's sort of the minimum that you should have for a measure of dispersion. Okay, so let's, so notice this is an if and only if. So I'm going to have to show them both ways. So first, assume that the sample standard deviation is 0. Then I'll show that the observations are all the same. After I've done that, then I'll go in the other direction. I'll assume that all observations are the same and show that the sample standard deviation is 0. Okay, so let's prove this. If the sample standard deviation is 0, then the variance is 0. But if the variance is 0, then by definition, the sample variance is the sum of x minus x bar, quantity squared, over n minus 1. Oh, let me assume that n is greater than 1. If n is equal to 1, then usually, so then the formula doesn't make sense actually. If n is equal to 1, then, meaning that you only have one data, then usually in this definition of the standard deviation, we just say the standard deviation is 0. So, you know, if it doesn't make sense, then we just let it equal 0 because it's a measure of dispersion. So if n is equal to, so I'll make the assumption here that n is greater than 1. Therefore, I can divide by n minus 1. I'm not dividing by 0. And so the sum of x minus x bar, quantity squared, over n minus 1 is 0. Multiply both sides of my equation by n minus 1. So that, well, 0 times n minus 1 is 0. So this says that the sum of x minus x bar, quantity squared, is 0. But let's think about this. X minus x bar, quantity squared, can never be negative. It's something that's square. If you take a number and you square it, you don't ever, and of course I'm assuming real numbers, you are never able to get a negative number out of that. So you're adding up a whole bunch of things that are never negative. The only way that the sum of a whole bunch of non-negative numbers is 0 is if they're all 0. You know, if you take 5 plus 4 plus 3 plus, 2.8, and you get that the sum is 0, the only way to make that 0 would be to be able to subtract something, but you can't subtract anything. You can only add something that's non-negative. Therefore, all those numbers had to be 0. So I must have that x minus x bar is equal to 0 for all x. Therefore, I must have that x is equal to x bar for all observations. But that means that since they're always equal to x bar, that's one number. So x is always equal to the same value, x bar, for all observations. Therefore, all observations are the same. And that's what I wanted to show. So next, if all observations are the same, then eventually I want to show that s is equal to 0. Well, if all observations are the same, suppose they're equal to something. Let's call it k. So or in this case, let's call it x. Sorry. So let's call that mutual value that they're all equal to. Let's call it x. So the sample mean is just the sum of all this data values. In this case, they're all equal to x divided by n. But since x is a constant, then I'm adding a whole bunch of constants. So it's just equal to n times x. The n's cancel. So I get that x is equal to x bar. So x minus x bar is always going to equal 0. Therefore, x minus x bar squared is always equal to 0. Therefore, the sum of x minus x bar squared is 0. I can divide it by any non-zero number. Let's call it n minus 1. Therefore, the sum of x minus x bar squared over n minus 1 is 0. Take the square root of that. Therefore, I have that s equaling the square roots of x minus x bar quantity squared over n minus 1 is equal to 0. And that's what I wanted to show. So this is sort of the minimum that we want for a measure of dispersion, that s equaling 0, that if this measure of dispersion is 0, then all the data, then all of the observations are the same. And we also have, if you remember from the previous section, that the sum of the square deviations was minimized when we were doing the sum of the square deviations for the mean. Therefore, and of course, you can divide that by a constant, let's say n minus 1. So that's minimized when we are looking at the dispersion from the mean, which means that if I take differing sets of data, differing samples, that it will change in the least amount that it can change. So when you take samples, every time you take a different sample, you're not going to always have the same numbers. So you don't want that measure of dispersion varies wildly. If it does, it's not a very useful measure of dispersion. Sometimes you get a 12, but another time, and just due to the fact that these chance variations, you get something like 1 billion. Well, that's not good. You want that when you take these random samples, that the value that you get is something that's reliable. And so this is reliable, and it does measure dispersion. So good. Next. If x, maybe, let me look if, I probably did this in my other, do I have, let's see, 2. Let me look at this one. Yeah, I bet you it's better. My notation's probably better here. Let's look over here. Okay. Yeah, this is a better notation. Okay, so it's the same sort of thing that I have on my other lecture notes, but I didn't update the lecture notes so it doesn't look as nice. So my notation is nicer in this. So let's recall some formulas. Oh, I still had it written this way. I don't like it written this way. Why did I write it this way? Oh, I still have it written this way. Okay. At the end, I should have written it some other way. Okay, so let's recall. So these are formulas from Math 125. And now they're actually, so this is some stuff that you should remember from junior high. And they also repeat it in high school. The following formulas. That the sum, and so I gave it to you, and maybe I should include these. Wait 1 second. Let's see if I can edit for 1 second. Let's see. I can edit this. Oh, good. It's deciding slowly but surely to do it. Come on. Sorry. So let me write it in the formula that you will. Don't worry about what I'm writing. So, and do I want to do it as a, yes, I will, as a population. Okay. I want to do it as a population. Oops. Oh, then let's do the other formula. Sorry. Just take me another second to write it in the notation I want. Okay, good. Don't worry about what I just wrote. Okay, so now let me save it so you can see it. Okay.
Professor,
Yeah.
I was taking a look of just before you started the proof, and I'm not sure if the formula, no, the formula is correct, but the procedure of standard deviation is wrong because n it's equal to 7, I think, on the standard deviation for the when you did the using the formula instead of the computation.
Which one are you referring to?
Just a little bit more above that one. Yeah. So
This
it's
one?
n. Yeah,
2,
it's
4,
n not
6,
supposed.
7.
Yeah, n not supposed to be
Oh,
7,
7.
not 9.
Yeah. Oh, then this is wrong. 2, 4, 6, 7. Unless, oh, maybe I didn't write all the numbers down. Is that what it is? Oh, I don't know. I'll check. Okay, so something's wrong here. Okay, is all I know. Okay, so something's wrong there, and oh, because this data is different from that. Okay, so I'll have to look. So something's wrong. What you're saying is something's wrong here. Yeah, something's wrong
Yeah.
there. Okay. Yay. Okay, so I'll look at it. Okay, so something's wrong, and I'll have to look at that. Okay. Wait 1 second. Sorry. Let me just put a quick note, because for some reason, at the end of class, I'll remember that something is wrong. I just won't remember what is wrong. 2, 4, 6, 7, and that. So this is wrong. Hopefully, I'll be able to see this. So, okay, so hopefully I'll be able to see this, and I'll change it. Okay, thank you very much. So there's something wrong there, and I gotta do it. Okay, I'll go past that wrong. Yeah, that's it. Thank you. That is wrong. Okay, so let's see. So let's do the following. So recall these formulas from Math 125. Which was in your Algebra 2. Actually, they gave it in Algebra 1, Algebra 2, and they also gave it in your algebra class that they give you currently in junior high, both 7th and 8th grade now. I think that's too early for you guys, but that's where they currently have these formulas. So the formulas are the sum I equaling 1 to n of I is n times n plus 1 over 2. The sum of I equaling 1 to n of I squared is n. And of course, I wrote that wrong. N times n plus 1 in parentheses, 2n plus 1. And that's I should be, okay. And so this is written in statistical notation will be that the sum of x is equal to n plus 1 over 2, or the sum of x squared is n plus 1, 2n plus 1 over 6. So I'll in case you guys don't remember these, I'll rederive these in a slightly more modern notation. So these were derived by Carl Friedrich Gauss. So you're going to be hearing more about Carl Friedrich Gauss in the near future. So this is not the first, will not be the last time that you hear of his name. So he first did this. This is really the first thing where people started to take notice of him. So when he was 10 years old, either 9 or 10, now I don't remember. I think it was 10 years old. So when he was 10 years old, he was in class, and his teacher decided to give his pupils a problem that he thought would take them forever to do, so that he wouldn't be bothered by these little children. And so he put up on the board, add the following: 1 plus 2 plus 3 plus ... plus 100. So add up those, the first 100 numbers. And then he turned to walk back to his desk, and immediately little Carl jumped up and down. He's a little kid at this point, and he says 5,050. And so he was able to figure this out, and he then, being only 10 years old, was able to figure out a whole bunch more very interesting things, the rest of what we're doing in this, these other formulas over the weekend. So let me show you more or less how a 10-year-old kid thinks. So he actually did these he did these in a different way. And so this is going to be a more modern way of deriving how we thought of, deriving the results. Not how we thought, but the results. So first, So actually, this this derivation is actually a derivation that I did. So this is a derivation that I did when I was a little kid for these formulas. So when I was like, 9 or so, 9 or 10, it's my derivation, which I thought was unique, but obviously it's not. But my notation was horrible. So it's my derivation, but in real proper notation. Okay, so let me do the following. And so this will be called, this property that I'm going to first show you is something called a telescoping series. And so, lemma. Let f take whole numbers to real numbers. Then the sum I equaling 1 to n of f at I minus f at I minus 1 is just f of n minus f sub 0. And this is true for all natural numbers n. So what this means is if you add up a whole bunch of terms, and if all the middle terms cancel, then the only things that remain are the first and last terms. So let's show the initial case. Show the case that this is true when I replace n by 1. So the sum I equaling 1 to 1 of f sub I minus f sub I minus 1 is, well, let's plug in 1. So this is f at 1 minus f of 0. But f of 0 is what I want, and n is equal to 1, so f of n is f sub 1. So therefore, I've shown that this formula works when capital N is equal to 1. So now let's show the induction case. So let's suppose that the sum I equaling 1 to n of f sub I minus f at I minus 1 is equal to f at n minus f of 0. Let's show that the formula then works when I replace n by n plus 1. And so let's look at the sum I equaling 1 to n plus 1 of f of I minus f of I minus 1. Well, it's going to be the sum of these first n terms plus the last n plus first term. So it's the sum I equaling 1 to n f of I minus f of I minus 1 plus, plug in n plus 1, f of n plus 1 minus f of n plus 1 minus 1, which is f of n. But I know that this term here, by the induction hypothesis, is f of n minus f of 0. And this last term is f of n plus 1 minus f of n. The f of n's cancel, so you just get f of n plus 1 minus f of 0. Therefore, this formula works when I replace n by n plus 1. Therefore, the induction case holds. Therefore, by the principle of mathematical induction, the sum I equaling 1 to n of f of I minus f of I minus 1 is f of n minus f of 0. And this holds for every natural number n. So now let's show that the sum I equaling 1 to n of I is equal to n times n plus 1 over 2. So let's look at the following. So if you have an I, well, if you have some power, first power, let's do one more power. So the trick is to go one higher. So the sum I equaling 1 to n of I squared minus I minus 1 squared. Well, again, by the special product formula, I minus 1 squared is I squared minus 2i plus 1. I have a minus sign, so let me change all the signs in the parentheses. So I get a minus I squared plus 2i minus 1. The I squareds cancel. So this is just the sum I equaling 1 to n of 2i minus 1 by the properties of summation. This is equal to 2 sum I minus sum of 1. But the sum of 1 is n. Therefore, I get that this is equal to 2 sum I equal 1 to n of I minus n. By the previous lemma, we have that the sum I equal 1 to n of I squared minus I minus 1 quantity squared is just n squared minus, well, 1 minus 1, which is 0 squared. So this is just equal to I squared, just equal to n squared. Okay. And so since this is equal, since these are the same, I just expanded them using one special product formula to the lemma that I have from above, then these two must be equal. So this must be equal to, so the 2 sum of I minus n must equal n squared. So I have 2 sum I equal 1 to n of I minus n equals n squared. Add n to both sides of my equation. So 2 sum I equaling 1 to n of I is equal to n squared plus n, factor out n, so it's n times n plus 1. Therefore, the sum I equal 1 to n of I is equal to n times n plus 1 over 2. And that's what you wanted to show. Next, let's derive the sum I equal 1 to n of I squared. Show that it's equal to n plus 1 times 2n plus 1, all over 6. So this is equal to, well, the sum I equal 1 to n of I cubed minus I minus 1 cubed will equal, using the special product formula, I minus 1 quantity cubed is I cubed minus 3I squared plus 3I minus 1. Changing all the signs inside the parentheses, I get minus I cubed plus 3I squared minus 3I plus 1. The I cubes cancel. So this is just equal to the sum 3I squared minus 3I plus 1. By the property of summation, this is just 3 sum of I squared minus 3 sum of I minus sum of 1. Sum of 1 is n. I know I just derived the formula for the sum of I. It's n times n plus 1 over 2. Let's simplify that. So multiplying the 3n minus 3n inside the parentheses and dividing by 2, I get a minus 3 halves n squared. Multiplying the negative 3n inside the parentheses divided by 2, I get minus 3 halves n plus n. Well, n minus 3 halves n is 1 half n. Therefore, I get that the sum of, well, of x, the sum I equal 1 to n of I cubed minus I minus 1 cubed by the above lemma, it's a telescoping series, is just n cubed minus 1 minus 1 cubed. And so I just get n cubed. Therefore, this sum is the same as this sum. So therefore, this 3 sum of I squared minus 3 halves n squared minus 1 half n must equal n cubed. Oh, let's get rid of all the fractions. So let's multiply everything here by 2. So I have that 6 sum of I squared minus the 2's cancel, 3n squared, the 2's cancel, minus n equals 2 n cubed. Therefore, bringing the 3n squared and the n to the other side of my equation, I have that 6 sum I equal 1 to n of I squared is 2n cubed plus 3n squared plus n. Factor out n. So I get n times the quantity 2n squared plus 3n plus 1. Factor what's in the parentheses. And so I get n plus 1 times 2n plus 1. Divide both sides of my equation by 6. Therefore, the sum I equaling 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. So now This is all the preliminary stuff. Now I can solve what I wanted. So now that I know this, I can show this. So this is all the preliminary stuff. And so I have the sum of x is n plus 1 over 2. Let's use that to show this. And so I have here that mu equals the sum of x over n, but the sum of x is just n times n plus 1 over 2. N's cancel, so this is just n plus 1 over 2. So I'm done. Next, sigma squared, by the simplifying computational formula, is just n sum of x squared minus the sum of x quantity squared over n squared. But the sum, so this is just n divided by n squared, is just 1 over n. The sum of x squared is just n, 2n plus 1, 2n plus 1 over 6. This is just the sum of x squared over n squared, but the sum of x is just n plus 1 over 2. Square that. So I just get an n squared, the n squareds cancel, times n plus 1 squared, all over 2 squared, which is 4. The n's cancel here, so this is n plus 1, 2n plus 1 over 6. I have two differing denominators. So in order to add two fractions, I have to find a common denominator. The common denominator in this case is 12. So let's multiply and divide by 2. Multiply and divide this term by 3. I have a n plus 1 in common, so let me factor that out. And my common denominator is 12. What remains is, well, let's multiply a 2 inside the parentheses. 4n plus 2. Multiply negative 3 inside the parentheses. So negative 3n minus 3. 4n minus 3n is n. 2 minus 3 is a negative 1. I have, again, a special product formula. The product of the sum and difference of two terms is the difference of their squares, n squared minus 1 over 12. And that's what I wanted to show. So sigma is equal to the square root of n squared minus 1 over 12. Let me go back to my Word document. Okay, so the variance of x plus a is just the variance of a. The variance of x plus a is the variance of x, where a here is a constant. So let's show that. So the variance of x plus a, by definition, is the sum of x plus a minus expected value of x plus a quantity squared all over n. The expected value of x plus a is just the expected value of x plus a from the previous section. Let me bring the negative sign inside the parentheses. So this is minus the expected value of x minus a. The a's cancel. So this is just x minus the expected value of x quantity squared over n. The expected value of x is just mu. So this is the sum of the square deviations from the mean divided by n, which is the variance of x. And that's what you wanted to show. Similarly, and it's really the same idea, the variance of x plus a for any constant a is the variance of x. So really the only difference is, well, changing uppercase to lowercase. Instead of having an n here at the bottom, I'll have an n minus 1 here at the bottom. So the variance of x plus a is the sum of x plus a minus expected value of x plus a quantity squared over n minus 1. By the previous section, the expected value of x plus a is the expected value of x plus a. Let me distribute the negative sign inside the parentheses. And so this is just equal to minus the expected value of x minus a. Well, the a's cancel. So this is just x minus expected value of x, the sample mean, squared all over n minus 1. But that's the variance of x. And that's what I wanted to show. Next, the variance of x minus a is the variance of x. Well, and this is true for any constant a. Actually, I've already shown this because I didn't make any assumption about the sign of A. And so A could have been positive or negative. And remember that adding the opposite is the same as so adding the opposite is the same as subtracting. And so I could just use property 5 to show this directly. But let me prove it anyway without using property 5. So the variance of x minus a is the sum of x minus a minus expected value of x minus a, quantity squared over n. And so by the properties of the mean from the previous section, the expected value of x minus a is just the expected value of x minus a. Again, distributing the minus sign inside the parentheses. This is just the minus expected value of x plus a. A's cancel. So this is just x minus a in the parentheses. And so we have that this is equal to the sum of x minus mu quantity squared over n. But again, that's just the variance of x. And so let me do property 8. And so in property 8, we have that the sum of x minus a is the variance of x. And we have that this is true for all constants a. Again, just by using property 6 in the fact that subtracting the same as adding the opposite. Property 8 falls directly from this, but I'll just prove it as if I did not know that. So the variance of x minus a is the sum of x minus a minus expected value of x minus a quantity squared over n minus 1. And so this is equal to, well, distributing the minus sign inside the parentheses. Using the fact that the expected value of x minus a from the previous section is expected value of x minus a. Distributing the minus sign inside the parentheses, I get minus expected value of x plus a. A's cancel. So I get x minus expected value of x inside the parentheses. But the expected value of x is just the sample mean. So this is equal to the sum of x minus x bar quantity squared, all divided by n minus 1. But that's equal to the variance of x. 9. And so let's show property 9. Again, you could use, in my notes I see previously, I just used the fact that we've shown this for the variance, but I'll prove it as if I didn't notice that I'd proven things before. So the standard deviation of x plus a is just the square root of the sum of x plus a minus expected value of x plus a, quantity squared all over n. By the properties of the mean from the previous section, I have that the expected value of x plus a is just the expected value of x plus a. Distribute the minus sign inside the parentheses. So this is equal to minus expected value of x minus a. The a's cancel. And so I just get inside the parentheses x minus the expected value of x, which is mu. And so I have that this is the square root of the sum of x minus mu squared over n, which is just the standard deviation of x. Similarly, again, this falls from our properties of variances. The standard deviation of x plus a is the standard deviation of x. And so the standard deviation of x plus a is the square root of the sum of x plus a minus expected value of x plus a quantity squared all over n minus 1. Well, the expected value of x plus a by the properties of the mean from the previous section is expected value of x plus a. Distribute the minus sign inside the parentheses. I get that this is equal to minus the expected value of x minus a. The a's cancel here. So this is equal to the expected value of x minus a. And the expected value of x is just the sample mean. And so this is equal to the square root of the sum of x minus x bar quantity squared over n minus 1, which is the standard deviation of x. Next, the standard deviation of x minus a is the standard deviation of x. And this is true for all constants a. And so the standard deviation of x minus a is the square root of the sum of x minus a minus expected value of x minus a quantity squared all over n. So this is the square root of x minus a minus expected, and again by the properties of the mean from the previous section. This is equal to, well, expected value of x minus a, distributing the minus sign inside the parentheses. This is minus expected value of x plus a. A's cancel. So this is x minus expected value of x, which is just mu. And so this is the square root of the sum of x minus mu squared over n, which is the standard deviation of x. Next, the standard deviation of x minus a is the standard deviation of x. Well, the standard deviation of x minus a is the square root of the sum of x minus a minus the standard minus expected value of x minus a quantity squared over n minus 1. By the properties of the mean from the previous section, the expected value of x minus a is the expected value of x minus a, distributing the minus sign inside the parentheses. This is just minus the expected value of x plus a. A's cancel. So this is just x minus the expected value of x. The expected value of x is just x bar. Therefore, this is equal to the square root of the sum of x minus x bar squared over n minus 1. But that's just the standard deviation of x. And that's what we wanted to show. Okay, so now I see at the end we're going to do it also. So I'll keep on this for a little while. So the variance of ax is just a squared times the variance of x. So the variance of ax is just the sum of ax and the expected value of ax quantity squared over n minus 1. But by the properties of the mean from the previous section, this is just equal to a times the expected value of x. I can factor out an a. I can factor out the a squared out in front of the summation. But the expected value of x is just x bar. So this is equal to a times the sum of x minus x bar quantity squared over n minus 1. That's just the variance of x. So this is equal to a squared times the variance of x, and that's what I wanted to show. Next, the variance of ax is a squared times the variance of x. It'll be the exact same proof that we just did above. The variance of ax is equal to the sum ax minus expected value of ax quantity squared all over n. Expected value of ax by the properties of the mean from the previous section is just a times expected value of x. I can factor out an a squared, bring it out in front of the summation. So this is equal to a squared times the sum of x minus the expected value of x, quantity squared, over n. But the expected value of x is just mu. And so this is equal to a squared times the sum of x minus mu quantity squared over n, which is just the variance of x. So we have shown that this is equal to a squared times the variance of x. And that's what you wanted to show. The variance of a divided by x is the variance of x over a squared, so long as a is not equal to 0. You don't want to certainly divide by 0. Actually, this is a form that is very useful. It's a form that we're going to be using quite often in the next few sections. In the future, I'll just say. So, again, we could prove this just using the properties of the fact that multiplication, division is the same as multiplication by reciprocal. So the variance of x over a is the sum of x over a times minus the expected value of x over a quantity squared divided by n minus 1. By the previous section, the properties of the mean, the expected value of x over a is just the expected value of x divided by a. I can factor out an a squared. Well, I can factor out 1 over a squared from the numerator and bring it out in front of the summation. And well, the expected value of x is just x bar. Therefore, I've shown that that the sum of x minus x bar quantity squared over n minus 1 divided by a squared, which is the same as, well, the numerator is just the variance of x. So there's the variance of x divided by a squared, and that's what you wanted to show. Next, the variance of x over a is the variance of x divided by a squared. Again, so long as a is not equal to 0. So the variance of x over a is the sum of x over a minus the expected value of x over a quantity squared, all divided by n. By the properties of the mean, the expected value of x over a is the expected value of x divided by a. Factor out what's in common, a, since it's squared, so factor out your a squared. And so bring that out in front of your summation. You note that the expected value of x is just mu, and you note that this is just the variance of x. So we have that this is equal to the variance of x divided by a squared, and that's what you wanted to show. The standard deviation of ax is the absolute value of a times the standard deviation of x. We could show this just using these facts that we've proven above, but I'm not going to use that fact. So the standard deviation of ax is the square root of the sum of ax minus the expected value of ax quantity squared, all over n minus 1. By the properties of the mean from the previous section, the expected value of ax is just a times the expected value of x. I can factor out an a from each of these inside the parentheses. I can factor out a squared from this term and bring it out in front of the summation. The square root of a squared is just absolute value of a. What remains is, and using the fact that the expected value of x is the sample mean, what remains is the square root of the sum of x minus x bar quantity squared over n minus 1, but that's the standard deviation of x. And so I've shown that this is equal to the absolute value of a times the standard deviation of x, and that's what you wanted to show. Next, the standard deviation of ax is equal to absolute value of a times the standard deviation of x. And so the standard deviation of ax is just the sum of ax minus expected value of ax quantity squared over n. But the expected value of ax is equal to a times expected value of x, using the properties from the previous, of the mean from the previous section. I can factor out an a from each of these inside the parentheses. I can factor out an a squared inside the summation. Bring the a squared outside the summation. The square root of a squared is just absolute value of a. What remains is just the standard deviation of x, given the fact that the expected value of x is mu. And so I've shown what I wanted to show. Next, The standard deviation of x over a is the standard deviation of x divided by the absolute value of a. So again, so long as a is not equal to 0. So the standard deviation of x over a is the square root of the sum of x over a minus the expected value of x over a quantity squared divided by n minus 1. By the properties of the mean from the previous section, the expected value of x over a is the expected value of x divided by a. I can factor out the common denominator a inside the parentheses since it's squared. Factor out the fact that it's 1 over a squared, bring that out in front of the summation. And so this is the 1 over a squared has been factored out of the summation. The square root of 1 over a squared is 1 over the absolute value of a. The expected value of x is just x bar. The square root of the sum of x minus x bar squared over n minus 1 is just the standard deviation of x. Therefore, I've shown that this is equal to the standard deviation of x divided by the absolute value of a, and that's what I wanted to show. Lastly, the standard deviation of x over a is the standard deviation of x divided by the absolute value of a, so long as a is not equal to 0. So it's the standard deviation of x over a is just the square root of the sum of x over a minus the expected value of x over a quantity squared divided by n. The expected value of x over a is just the expected value of x divided by a using the properties of summation from the previous section. And so I can factor out an a from the denominator. I can, this is being squared, so I can, so this is just divided by a squared. And I'll bring that out in front of the summation. The square root of a squared is the absolute value of a. So I'm dividing by the absolute value of a. What remains is, since the expected value of x is mu, is the square root of the sum of x minus mu squared, all divided by n, which is just the standard deviation of x. Therefore, I've shown that this is equal to the standard deviation of x over the absolute value of a, and that's what I wanted to show. Good. Pooled variance. So I guess in my lecture notes, I'd use the previous facts. So pooled variance. To compute the pooled variance for two samples, compute the weighted mean of their variances, where you're being weighted by their corresponding degrees of freedom, mu1 and mu2. So the pooled variance is equal to mu sub 1, s of 1 squared, plus mu sub 2, s of 2 squared, all divided by mu sub 1 plus mu sub 2. So this will be a important formula that we'll be using in chapter 9, I think. I think it's chapter 9, I'm pretty sure, and chapter 11. So in later chapters. So this is an important formula that will be used in later chapters. Skewness. A distribution of data is skewed if it is not symmetric and it extends more to one side than the other. It is asymmetric. It is not symmetric. A distribution of data is symmetric if, let's say, the left half is a mirror image of the right half. Just like what we did back in section 3.1, where we extended these concepts of a mean, of the measure of central tendency to dealing with frequency distributions. We can also do that for these measures of dispersion. the standard deviation. So the standard deviation for a frequency distribution, the sample standard deviation for a frequency distribution, is just the square root of the sum of f of x minus x bar quantity squared, all divided by n minus 1. Or if I use the simplifying computation formula, it's a square root of n times the sum of f of x squared minus the sum of f times x quantity squared, all divided by n times n minus 1. The population standard deviation, sigma, is the sum of, is the square root of the sum of f x minus mu squared over n, is the square root of n sum fx squared minus sum fx quantity squared, all divided by n squared. So let's let's do this for an example. Determine the sample standard deviation for the following frequency distribution. So 3 2s, 4 3s, 2 4s. Let's attach 2 additional columns. The fx column, fx squared column. And so multiply first and second column to get the third column. 2 times 3, 6. 2 times 6, 12. 3 times 4, 12. 3 times 12, 36. 4 times 2, 8. 4 times 8, 32. Add 9, 26, 80. So s squared is equal to n, 9, sum fx squared, 80, minus sum fx, 26 squared, divided by n, 9, times n minus 1, 8. So you get 11 out of 18. Take the square root of it to get the sample standard deviation. 0.78173596. So let's suppose we have, oops, the following, so 2, 3, 4, and 3, 4, 2. Good. Okay, let's get out of here. So let's find the standard deviation. So to find the standard deviation, go to math, PRB, wait, go to lists, go to list, math, standard deviation. I was thinking of something else. And to L1, comma L2. Point 78173596. Standard deviation for a group frequency distribution. Again, the same that we did in the previous section. So the sample standard deviation, S, is equal to square root of the sum of f x sub cm minus x bar squared, all divided by n minus 1. The square root of n, sum fx squared, fx sub cm squared, minus the sum fx sub cm quantity squared, all divided by n times n minus 1. The population standard deviation, sigma, is equal to square root of the sum of f x sub cm minus mu quantity squared, all divided by n. It is by the simplifying computational formula. the square root of n sum fx sub cm squared minus fx sub cm quantity squared, all divided by n squared. Determine the sample standard deviation for the following group frequency distribution. 3 numbers between 10 and 20, 4 between 20 and 30, 2 between 30 and 40. So first, so here I have my group frequency distribution. First, let's determine the class marks. And so to determine the class marks, let's add and divide by 2. And so 10 plus 20 is 30, divided by 2 is 15. Twenty divided by 30 is 50, divided by 2 is 25. 30 plus 40 is 70, divided by 2 is 35. So here are my class marks, 15, 25, and 35. Next, let's attach 2 additional columns, the fx sub cm column and the fx sub cm squared column. And so let's multiply first and third column to get the fourth column. 15 times 3, 45. 15, then multiply first and fourth column to get the fifth column. 15 times 45, 675. 25 times 4, 100. 25 times 100, 2500. 35 times 2, 70. 35 times 70, 2450. And let's add 9, 215, 5,625. So let's compute the sample variance, n, 9. Sum fx sub cm squared, 5625, minus sum fx sub cm, 215 squared, divided by n, 9, n minus 1, 8. And so take the square root of that. So S is equal to 7.8173596. Okay, so let me do this. So the TI-84. So we want 15, 25, 35. And all the frequencies are the same. Okay, so I want to determine the standard deviation. And it is 7.8173596. So range rule of thumb. So we're going to be interpreting. So I've given you some examples involving the state. Well, I've given you a definition of these measures of central tendency. I'm sorry. I've given you these definitions of these measures of dispersion. I've given you some properties of them, and I've given you some examples, mostly involving, of course, the standard deviation. Now let me give you some interpretation for this idea of a standard deviation. So first, so how to interpret a standard deviation? The range rule of thumb, the empirical rule, Chebyshev's theorem, and standardization, the standard scores, the z-scores. So The range rule of thumb. So the range rule of thumb says, well, maybe I'll say it this way first. So the range rule of thumb says that in most cases, your standard deviation is approximately the range divided by 4. So it turns out that if you don't know a lot about the data, you can actually just use the range and give a good estimate for what the standard deviation is. You just divide it by 4, the range divided by 4. So that's true in the vast majority of cases. There are some cases where it's not quite true, but usually the range over 6 will give you a good estimate for your standard deviation for those remaining cases where the range over 4 rule doesn't quite work. So informally, so now I can, well, how can I sort of give this to you in a different sort of idea? So informally, we can think of usual values as those that are typically values that you'll see, a typical range of values. Well, we've got a range here. And so that means that the range is 4 times the standard deviation. Therefore, a rough estimate for the minimum value, or let's say maximum value, for the maximum usual value is that it's 2 standard deviations above the mean. And for the minimum value is 2 standard deviations below the mean, because the range is 4 standard deviations. So I can say that if you ask me what's the maximum usual value, oh, that's easy. It is the mean plus 2 standard deviations. What's the minimum usual value? Well, it's the mean minus 2 standard deviations. So let's do an example. Using the 40 chocolate chip counts for Chip Ahoy cookies, the mean is 24 chips, and the standard deviation is 2.6 chips. Use the range rule of thumb to find the minimum and maximum usual number of chips. Would a cookie with 30 chips be unusual? Well, let's look at the minimum usual value. The mean, 24, minus 2 times the standard deviation, 2.6, 18.8. The maximum usual value, the mean, 24, plus 2 times the standard deviation, 2.6, 29.2. So 30 is actually above 29.2. So because of this, because 30 falls above the maximum usual value, then we would consider 30 to be a cookie, a cookie having 30 chips as being a cookie with an unusually high number of chips. The empirical rule. So the empirical rule says that if you happen to have a distribution that is approximately normally distributed, approximately bell-shaped. So if it looks like a distribution that looks approximately like this curve, then the following will hold. That 68% of your data values lie within 1 standard deviation of the mean. 95% of your data values lie within 2 standard deviations of the mean. Virtually everyone, 99.7% of your data values lie within 3 standard deviations of the mean. Now, suppose I don't know what the distribution looks like. Or I do know what the distribution looks like, and it's not bell-shaped. So what do I do if I have a distribution that's not bell-shaped? Or if I don't know that the distribution is bell-shaped, what do? Well, I'll use Chebyshev's rule. Chebyshev is a very famous mathematician around the turn of the century, meaning from the late 1800s to the early 1900s. Very famous mathematician. And he was obviously Russian. And he wrote in Italian, German, French, well, of course, Russian, Italian, German, French, Polish, I don't know, I think Romanian and Hungarian, English. I think that's about it. Yeah, so he wrote in a lot of different languages. And when he wrote in, except for in Russian, so, well, I'll say that. When he wrote in any differing language, because of the way that, you know, it doesn't use, so they use the Cyrillic alphabet, the Russians. And so they don't have quite the same letters we do. Well, the other languages that he wrote in, they don't have the same letters. So because of that, you have to, you know, make little guesses. You know, what do I want? For this letter, what letters do I substitute in that other language? And so because of that, in every language that he wrote, and he wrote in so many different languages, every time he wrote in a different language, he would translate his, you know, his name and write it in a slightly different way, you know, according to the sounds of the language that he was writing in. So if you look for the word Chebyshev's, you know, obviously if you write it like in English or whatever, using, you know, our alphabet, you will probably see at least 8 or 9 different ways that his name is spelled. So think of every different ways that you can sort of, you know, spell in whatever language you want, or in any language you want. All those different sounds are, you know, all those sounds make any sort of letters that look like that. If it looks like Chebyshev, it's him. So just because it's many different spellings, you know, there could be T's here, there could be some SHCHs here, some I's, some B's, some V's. So any sort of variation of this spelling is probably him. So he's really, yeah. So any of those, you know, variations will be this person's name. So I do not guarantee that if you look in a different book and you look at Chebyshev's rule, that it's not spelled differently. I almost guarantee it's probably spelled differently, because everyone has their favorite ways of spelling his name, due to the fact that he spelled it so many different ways. Okay. It's because he spoke so many different languages. He gave so many different variations to his name. Okay, so Chebyshev rule. For k greater than 1, at least 1 minus 1 over k squared of the data lie within k standard deviations of the mean. So let me assume that sigma here is greater than 0. If sigma is equal to 0, it really doesn't make sense. So we'll assume here that sigma is greater than 0. If sigma is 0, then then everything lies at the mean. So assume sigma here is greater than 0. Let A be the set of all x such that the absolute value of x minus mu is greater than or equal to k sigma. Then sigma squared Oh, and let's write P of X as F over N. So sigma squared is the sum of F X minus mu squared over N, or we can write it as sum X minus mu squared P of X. Well, let me divide the sum up into two pieces where either you're in A or you're not in A. So the sum for X in A of X minus mu squared P of X plus the sum X not in A of X minus mu squared P of X. Well, since P of X is greater than 0, greater than or equal to 0, and X minus mu, quantity squared, is greater than or equal to 0, then the sum, X not being in A, of X minus mu squared times P of X is greater than or equal to 0. Therefore, I can get rid of it. So therefore, this is greater than or equal to 0. So the sum, X in A of K squared, oh, and when X is in A, this is greater than or equal to K sigma. So this term here is also greater than or equal to the sum X in A of K squared sigma squared P of X. I can bring the K squared and the sigma squared out. So this is equal to the sum K squared sigma squared, the sum X in A of P of X. But this is just the probability that X minus mu is greater than or equal to K sigma. Divide both sides of my equation of my inequality by K sigma squared. So I have the probability that X minus mu, an absolute value, is greater than or equal to K sigma, is less than or equal to 1 over K squared. Therefore, taking the complementary event, the probability that X minus mu, an absolute value, is less than K sigma, is less than or equal to 1 over 1 minus K squared. So at least 1 minus 1 over K squared, the data, lies within one standard deviation, within K standard deviations of the mean. So let's do an example. IQ scores have a mean of 100 and a standard deviation of 15. That's by definition. So by definition, how do you figure out your IQ score? Well, you take the average of all adult males, adult Caucasian males in the United States, and you make that have an average of 100 and a standard deviation of 15. So by definition, that's what the IQ scores are made to have a average of 100 and a standard deviation of 15. So now, well, what can you conclude from Chebyshev theorem? Well, at least 75% of the IQ scores lie within 2 standard deviations of the mean. So at least 75% of IQ scores are between 70 and 130. So let's do 3 standard deviation. So 1 minus 1 over 3 squared. 1 minus 1/9 is 8 over 9. So at least 88.9% of IQ scores lie within 3 standard deviations of the mean. So 3 times 15 is 45 from 100. So at least 88.9% of IQ scores lie between 55 and 145. Given any set of data, at least what percentage of data values lie within 5 standard deviations to either side of the mean? So let's look at 1 minus 1 over K squared. Well, K is 5. 5 squared is 25. 1 minus 1 over 25. 25 minus 1 is 24. So 24 over 25. 0.96. So at least 96% of your data lies within 5 standard deviations of the mean. And that's for any set of data. So if I have any set of data, always 96% of the data will lie within 5 standard deviations of the mean. In a survey relating the mean time for a drug to take effect, a sample of 400 trials showed a mean time of 26 minutes with a standard deviation of 4 minutes. Obtain the minimum and maximum usual time using the range rule of thumb. So, minimum usual time, the mean, 26, minus 2 times standard deviation, 4. So 26 minus 8, 18 minutes. The maximum usual time, the mean, 26, plus 2 times the standard deviation, 4. 26 plus 8, 34 minutes. So the minimum usual time is, so it takes usually between 18 and 34 minutes for this drug to take effect. Please note, we never use 400. Just because it's a number doesn't mean you've got to plug it in somewhere. Students, when they see numbers, especially on exams, they feel compelled to plug in a number even when it doesn't make sense to plug it in anywhere. So just because it has a number doesn't mean you must plug it in somewhere. The z-score. So the z-score is, well, x minus mu over sigma. It is x minus mu sub x over sigma sub x. It is the number of standard deviations above the mean. So a z-score of 4 means you're 4 standard deviations above the mean. A z-score of -3 means that you're 3 standard deviations below the mean. So, comparing variation in different samples. So, if you want to compare 2 standard deviations, you should compare 2 standard deviations only when the sample means are approximately the same. Otherwise, when comparing variation in samples with very different means, then it is better to use the coefficient of variation. So if there's a lot of difference between the means, use coefficient of variation, or we can look at the z-score. So again, the z-score is the number of standard deviation that x is above or below the mean. So an outlier. So now we can define an outlier a little bit better. So an outlier is a data value that has a z-score greater than, whose absolute value is greater than 2. If your z value in absolute value is greater than 2, then we call you an outlier. Now, of course, there's never universal agreement, especially with sociologists. So sociologists always do things different than everyone else because there's so much. Well, because if they said 2 standard deviations is an outlier, they basically, everything varies a lot when you're talking about sociology. So usually in sociology, so they'll have different things that say, what they say. Oh, they have different rule of thumb also. So So what they say is their usual values or whatever is one standard deviation. So outliers are things that are above one standard deviation for sociologists. So a pulse rate is measured to be 48 beats per minute. Is the pulse rate unusual if the mean adult pulse rate is 67.3 beats per minute with a standard deviation of 10.3? So let's take the z-score, x minus mu over sigma. So x, 48, mu, 67.3 over sigma, 10.3. So I get a negative 1.873786408. Since this z-score is between plus or minus 2, then this is not an unusual pulse rate. Let's do another example. Kim takes an exam and gets a score of 64 on the exam. The mean score on this exam for Kim's class was 55 with a standard deviation of 2. Whereas Betty took a different exam in a different class, getting a score of 97 on the exam. The mean score for the exam for Betty's class was 96, the standard deviation of 3. The instructor for both Betty's and Kim's class had the following curve. A, if you are at least 2 standard deviations above the mean, you get an A. If you're between 1 and 2 standard deviations above the mean, a B. If you are between 1 standard deviation above and 1 standard deviation below the mean, you get a C. If you're between 1 and 2 standard deviations below the mean, you get a D. If you're more than 2 standard deviations below the mean, you get an F. So the question is, well, what grade did Betty get and what grade did Kim get? So let's look at Kim. So Kim got a 64. The mean was 55 and the standard deviation was 2. 9 divided by 2 is 4.5. She's 4.5 standard deviations above the mean. That is a very, very good A. And so, yes, that's definitely an A. Let's look at Betty. So Betty got a 97. The mean, and so mu is 96, sigma is 3. And so 1 over 3.3, which means that you are between plus or minus 1 standard deviation from the mean. Therefore, you have a C. So Betty, who got a 97 on the exam, got a C. So looking at the curve, Kim got an A with a score of 64, gives you an A, whereas Betty got a 97, and that gave her a C. Okay. Again, you live and die by a curve. It depends on what everyone else in class does. So it really doesn't matter how well you do, it's how well the class does. And so your grade is determined by the class. So usually what happens is when everyone in the class, or when people think everyone in the class is doing poorly, then they want a curve. They hate a curve when everyone in the class is doing well. They don't like a curve that much because things like this occur. Okay, that really finishes off